Okay. So today we'll be talking about the tight binding model in physics. And first, I'm planning to start with a review on Bloch's theorem, and then we'll talk about how to construct a tight binding Hamiltonian, and then some examples, and then move on to graphing. Okay. So the Bloch's theorem we talked about like 2 weeks ago, I think, something like that. And it basically states that if you have a Hamiltonian that is translationally invariant on your lattice, then you can find a basis of eigenvectors of H that are also eigenvectors of the translation operators, and then these eigenvectors will have the form of a plane wave times some periodic function which has the same symmetries as the lattice. So these states are identified with this vector k, which physically speaking is like the momentum vector. Right. So in the tight binding model, we assume that we have a lattice where the electrons can move to the site right next to it, but only the one site that's next to it. So you can't go 2 sites from where you are, but you can go like 1 site from where you are. So the Hilbert space, in that case, would have the vacuum state, which is there's nothing here, and then some states I, which is like where the electrons are. Then how would we hop from one site to the other is that we destroy an electron at this site, and then we create an electron at the site right next to it. So in terms of operators, we would make creation and annihilation operators at the site I. So how would they act on this Hilbert space is you can create an electron out of the vacuum, or you can destroy an electron into the vacuum. And a property of electrons is that, like, because of the Pauli exclusion principle, you can't have 2 electrons in the exact same state. So if one site is already occupied by an electron, if you try to create another electron at that site, you can't do this, so this would give you 0. And this 0 is not the same as the vacuum state 0. This is like if you try to destroy an electron in a site where there is already no electron. So basically, like in terms of occupation, at every site, your electron number is either 0 or 1. So you can't add another electron to something that already has 1 electron. And then technically speaking, there's also spin, but it's not really relevant in this discussion, so we're just going to ignore spin. Right. So if you're equipped with a Hilbert space like this, and your operators act like this, so what does your Hamiltonian of going from like a Hamiltonian that has the interactions of going from one site to another site look like?
Let's first stop and ask a question. What is the I and what is the 0 state?
There's a particle, there's not a particle.
Okay, correct. I is, yes, and when we write I, we mean I have some lattice, and then there's a particle on the ith site where I index these sites inside. Sorry.
So does anyone have an idea what the Hamiltonian might look like? What kind of form it will be? If we're writing down a Hamiltonian that describes an electron going from one site to the other site using these operators and these states, what do you think the Hamiltonian might look like?
So going from one site to another site, what happens? If I had an electron here, it moves to some site somewhere else, right? What happened? There was an electron here, and now there is there's an electron there, but is there an electron here?
Yeah.
No. Well, if it moves from here to here, right?
Like all the electrons, is it like outer shell or like all the electrons going?
Yes. So here, this is an important point. In this model, how many electrons are we considering?
N. Well, there's a total number of electrons.
Well, sure, but usually in these tight binding models, when you write down the Hamiltonian you're about to write down, you're always considering the motion of one single valence electron, right? And then you're assuming that all of the other electrons cannot move, and are kind of, say you only have one valence electron and it can hop from atoms, but then everything else is stationary. The atoms are perfectly stationary.
Right.
That's why it's called the tight binding model. The electron is tightly bound to the atom, and
right. So this Hamiltonian describes the interaction of one electron going from one state to another state. So physics speaking, if we have
So what else are we assuming about this electron? If you think about an atom, it has what? It has orbitals, right?
Right, it's going from the ground state to the ground state. Like it's going from the same shell, if you will.
Yes, same energy level to the same energy level. And so we're essentially making this assumption that, hey, my atom, my system is such that, okay, the thing is tightly bound to the atom. And so we can assume as an approximation that all of my states are just the nth energy level of an atom. So it can only hop from this energy level on this atom to the same energy level at this other atom. And this is a certain big approximation we're making. This does not work for all crystals and all materials, because in some crystals the electron is in fact not tightly bound to the atom. So you need the opposite. You need like a free electron model. But this is what we're kind of interested in.
So this is kind of like a toy model of that we're kind of making,
Yeah.
where the electron is very nice. So we write the Hamiltonian as there's some energy correlated to this electron hopping from one side to the other, and then you sum over neighboring sites I and j, which basically means if there's another site here, you're only summing over the sites that are right next to it. Like in terms of this site, you're only summing over the sites that are right next to it, not the site that's like one more from it, which is to say that the electron can only go from one side to the other. And then you have so this is to say, if I had...
So have them explain what it means. Why is that the Hamiltonian that represents this?
Suppose you had an electron at site I here. What would this Hamiltonian do to this to the state?
First, like add an electron on the other, like one electron go the other side, and then it goes back. I don't know. It's like AI plus an AJ.
Right, but these operators are creation and annihilation operators on one specific site. Like for these operators, this operator does not care how many other sites you have. It only cares about itself. So with this state, then we apply, so say we look at this term first. So AI destroys the electron at this state. And then, once you apply AI on this state, you get a vacuum state. And then when you act AJ dagger, which is the creation operator on the site J, you create an electron here. So, but this term, you started out with no electron in the J state. So if you destroy an electron in the J state, you get 0, and then like this 0, not the vacuum state 0. So this term does not act on this state. So what you've physically done is this state tells you destroy an electron here, create another electron here.
Which you said you should write it down.
How?
You just write it down.
Okay.
Write it down at the bottom, and then you can erase it or on the other board. That's too little space for that calculation. Come on. Do it somewhere at the bottom and then erase it if people understand. No, I mean just write down the calculation. Like AI, you have AJ dagger AI applied to the ith state, and write down what happens at each step.
Okay. So I feel like this might be bad notation, but let's say we represent the state with an electron at I and no electron as J as like just then when we act this on here, so we have A, J dagger, AI, the AI acts on the I state, which is this state here. Then you get So this step here destroyed the electron you already had at I. Then next step, when you act the AJ creation operator, this acts on the J state here. So then you get, this is equivalent to saying, okay, I had an electron here. This step, AI here destroys this electron. The next step, AJ here creates an electron here. I know it seems kind of convoluted, but I think like the way it's set up like this is to prevent if you have a state with like nothing there, like if you had a state with nothing there at all, then like if you start out with the I equals 0, J equals 0 state, this does not make electrons out of thin air.
Yes. So one thing you forgot to write down is that, well, maybe you had it written down, AI acting on the vacuum state.
Right. So the way
you also can't have two electrons in the same state on the same site by Pauli exclusion principle.
Right. So this formalism kind of just forbids you from creating things out of thin air or destroying things into thin air. Right. So now we stare at this Hamiltonian, and then are there any properties that it might show?
Okay, let's stop and first ask questions. Do people understand why this is the Hamiltonian? That will tell me about this idea that a particle can hop from here to here, and that costs some energy. Right? Like we told you what the Hilbert space is by making some physical assumptions, like either have no particles or have a single particle on site I. Right? And then we introduced these operators in this way, as written there, linear operators, very nice. And then we wrote down some Hamiltonian in terms of these operators that physically corresponds to a particle moving from one side to another side. And then, if a particle moves from A to B, that you can think of it as the particle being destroyed at A and being created at B.
Means like when an electron is destroyed at A, and then it needs the energy to like, I don't know how to describe it, but
Well, it needs some energy to tunnel to B. And the point is that in this model, we don't think about how this tunneling happens. We just think about it, it's some process that happens and costs some energy to you, right? Like you can look at a more detailed microscopic model where you think about like orbitals and think about how orbitals overlap. This model kind of forgets about all of that and says, bottom line, I know the electron can tunnel from this site to a nearest neighbor site. And that should cost some fixed amount of energy by assumption. Like you just keep simplifying your problem until it's so simple that it's literally just, electron can move from here to here. And then that's like the only interaction you really have. Not really an interaction. So are people following how this Hamiltonian physically means that? And how we wrote it down? Yes, no?
I see confused looks.
Yeah. If you're confused, you should say something. You should take a sip of tea so it's less awkward.
Yes.
I normally have a second cup, but the person borrowed it yesterday during lunch and never returned it.
Hunt them down.
What do you think I'm doing right after this? Okay. If something is unclear, you should ask questions.
Or give me a thumbs up if everything is clear. this is kind of an assumption that we're making, that this is not Hamiltonian, because this is the physical interaction that we want to describe. And then what is the Hamiltonian we can write down to describe this interaction? And this is kind of the only thing that like obeys the properties that we want for the physical process, because otherwise you start creating electrons out of thin air or destroying electrons into thin air.
So roughly, what are the physical assumptions we're making? We're making the assumption that the electron is tightly bound to the atom. So the electron can either be next to the atom, and it, or next to some atom, but it cannot be somewhere in between, because I don't know, for whatever reason this happens. Like say the attraction force of the atom in this particular configuration is very, very strong. So the electron can't be between atoms, right? So based on that assumption, we say that the Hilbert space has to be just the set of atomic states. Okay. That's the assumption. Then you say, okay, well, I know quantum mechanically that the electron can like tunnel. The electron will have some wave function, right? And then it can tunnel from one place to another, right? From one atom to another. Actually, let me maybe draw this idea with like a 1D chain. So the assumption is, okay, suppose I have some atoms, right? And it's a 1D lattice. So it's just some atoms in a line, okay? So these are my atoms. Okay, and then I have some electrons. Well, these atoms have some very strong negative potentials, right? Something like minus 1 over r, right? They have a strong attractive potential for the electron. Do you agree? So in some sense, so this is V, the potential, okay, and this is kind of my x direction. Do you agree? Okay. And so, suppose the electron is maybe in some, I don't know, fairly low energy state. So, the electron is kind of at this energy level. Do you agree? So clearly, it can't really spend much time here, because here there's a very high potential energy. It can't be spending much time here. So let's assume that the electron just doesn't spend any time here. It's always either somewhere here, or somewhere here, or somewhere here, or somewhere here. All right? Okay, does that make sense as a physical assumption to make? If the potential indeed looks like this. It doesn't always, but suppose it does. Okay, and so in that case, if the electron's always here, then we can say, okay, suppose it's say in the ground state, which is why, okay, it doesn't have a lot of energy. So let's just assume that it can only stay at the ground, it always stays at the ground state, let's say. Okay, and so then at each point I have at each point Ri, so this is I plus 1, I plus 2, I minus 1, okay. At each site, I have just the ground state that the electron can be in. Okay? But then quantum mechanically, I know that the electron can tunnel from here to here, right? Like you've done tunneling, say, through like a potential barrier, right? In 256 or something like this. You know that something, if you have a wave function here, it like decays exponentially and then continues here somehow. Right? So there is some tunneling probability and tunneling energy cost associated with it. So you say, okay, well, surely an electron tunneling from here to here, okay, it's possible, but it's going to be very, very, very unlikely. Do you agree? Because, I mean, it has to go so far, right? It will decay so much by this point. So you say, okay, let's neglect all tunnelings that are, too far away, and only include in our model tunneling that goes from here to here and from here to here. And so that's the next assumption here. You're assuming that, okay, so we assume that the electron is tightly bound to the atoms because the potential looks like this for some reason, and whatever the reason is. And then you say, okay, we're in the ground state energy, so that's the next assumption you're making. And then you assume, which would be a good assumption if you're, say, looking at like the low energy limit of a system. Like you're looking at some material at low temperatures. That would be valid. And then you're assuming what? and then you're assuming, okay, let's only think about tunnelings to the kind of nearest neighbor atom. Okay? Do you agree? And then you say, okay, all of these tunnelings, because looks very, very nice and symmetric, all of these tunnelings should have the same energy cost as long as you're tunneling to the nearest neighbor. And so you've made all of these simplifying assumptions and arrived at that Hamiltonian. Do the assumptions that I've stated, like, is it clear what assumptions we're making?
Yes.
Okay.
When you say we make the assumptions and then we get the Hamiltonian, there's
Yes.
a lot of work in that getting.
Well, yes, that's right. This is not a Hamiltonian that will describe every single crystal system. In fact, it applies only for certain crystal systems. But it does tend to work fairly well.
Because you say it works, and it
Well, it works because we made those assumptions.
Yeah.
So in the systems where those assumptions are hold, then that Hamiltonian should probably give you a good description. In the systems where those assumptions don't hold, it wouldn't.
I know. I'm just like wondering if there's like, how did we get to this Hamiltonian, like from those assumptions? Like, is there any logic that we're going to talk about? Or say, like, this is the thing.
Well, we said that, okay, the only process that can happen is this jumps from here to here, and that costs some energy, right? Okay, and so we write down a Hamiltonian where the only thing that's allowed is a particle going from one side to another, and that costs some energy. One thing that technically Janet forgot to include is you could include an additional kind of E0 term, which is the energy of kind of the ground state energy degree. But since we're assuming that all of our states are the ground state, then this is just a constant, and shifting the energy by a constant shouldn't change your physics too much, so you can remove this constant and not worry about it. So yeah, we've made many simplifying assumptions. In principle, if you want to read in Abrikosov, the book on normal metals, there is a discussion of how to, if you were to write down the most general Hamiltonian possible, how to keep making these assumptions and then reduce kind of the most general Hamiltonian to a Hamiltonian that looks like this. But then the problem is that's like, there's a lot to read there. It's like a couple pages and you have to be very careful with what you say. But the assumptions are still like essentially the same. It's the exact same assumptions, it's just they have a different starting point. But do people believe how this Hamiltonian would model this kind of situation? That's the important thing.
Like your Hilbert space is like whether or not you have an electron in one of these wells. And then these operators are what you can do if you do have an electron in these wells.
Okay, so yeah, do people see how that corresponds to this situation, at least in some level?
In some way.
Okay. That's fine. Let's move on, and then maybe it'll make a bit more sense.
I will erase this constant term because we don't like.
And you can
like
erase my as well.
No, I think this is nice. Okay, we start this Hamiltonian. This is a Hamiltonian that describes this system. Then one thing that we can notice about this Hamiltonian is that it has translational symmetry on the lattice sites. Does that make sense? So based on that, we can apply Bloch's theorem and say that the eigenstates of this Hamiltonian can also be characterized by some momentum vector. Then it makes more sense for us to rewrite this Hamiltonian in the momentum state basis. So instead of having creation and annihilation states in the position basis, we have creation and annihilation states in the momentum basis instead.
So why is this Hamiltonian translationally invariant? Okay, so you should say words. That's pretty close to the right answer, but you should say also a word with it.
It is translationally the same.
Well, okay, if I apply a translation, so how is it what's the condition? The condition is that translating the system has to commute with a Hamiltonian, right? The translation operator. Do you agree? Okay. So what happens if I translate the system? Yes, if I have like an infinitely long system, or if I add some periodic condition, if I apply the translation operator on this thing, what do I get back on this Hamiltonian if I compose that? If I have this infinitely long lattice and I shifted this by one unit to the right or to the left, what will you still see? What changed? Okay, nothing changed. Thank you.
Yes. So
Nothing changed.
yes. Which
So
is
the point is, if I apply the translation operator to H and compose them, what am I going to get back?
Same thing.
The same thing. Yes. Because I just shifted everything, but all of the we assume that all of the hopping amplitudes, hopping from one side to another, all of them were the same and equal to t anyway. Right? So if I translate along a symmetry of the lattice, I should get back the exact same thing. Now, this kind of assumes that I have like either an infinitely large lattice, which is of course not always the case, and it also assumes that I have, or alternatively, it assumes some periodic boundary condition, where you assume that my wave functions have to be periodic in some sense, or whatever. But so what does this suggest? Where would our model break down? Where do we expect to see something very different from this model? Yes, at the edge of your crystal, correct. So this is another thing. Like here, we're assuming this kind of periodicity coming from somewhere, but this periodicity is really something that we're assuming, for whatever reason. But it should maybe work if you're somewhere in the bulk of the crystal. But there could be something very different and very interesting happening on the edges, right? So this is another assumption we're making. Okay, go ahead.
Okay. One analogy that I think might be helpful is that this is a Hamiltonian that only cares about neighbors. So this is kind of like the equivalent of how if you have Coulomb's law between two electrons, you don't really care about where your origin is because your Coulomb's law only cares about the distance between the electrons. So no matter where you move your origin, you still have the same force between the electrons. I feel like this is kind of the same thing, right? Okay, so our next step from here would be that because we know that this is a translationally invariant Hamiltonian, we can apply Bloch's theorem to this Hamiltonian, and the eigenstates, the simultaneous eigenstates of the Hamiltonian and the translation operators are labeled by some k, which is like a momentum vector. So right now what we're going to do is we're going to move this position representation of the Hamiltonian into a momentum representation of the Hamiltonian. So these are the relations that the in position space that the operators obey. So we want some operators that in momentum space have basically the same kind of properties. I don't know if you guys went over this in quantum, but this is kind of just like a change of basis thing where you can add in like a resolution of identity of some. Does this make sense to everyone? Great. Right. Then, because we know that we want the momentum momentum space creation and annihilation operators to have the same sort of properties, we can write this K as the creation of some space from the vacuum. This is just a number. These are acting on the same vacuum state. So then we have that the position space creation operator is a sum over K of the momentum space creation operator with this factor here, which is basically like P of x, which is 1 over root. Basically a Fourier transform between position space and momentum space, right? So by the same logic, you can find, and you should check for yourself if you don't believe me, but differs by a negative sign, right? Can I erase this?
Yes.
So now what we do is we plug these formulas into this Hamiltonian and see what we get.
Make sure to move the camera so that things are visible.
I forgot one step. Okay. So initially we had the sum over I and j states. In a lattice where you have one set of translation operators to go everywhere you want, which is a Bravais lattice. But basically, lattice sites where you only need one set of lattice vectors to go to every single site. So this would be like triangular lattices. You can kind of just copy paste over all space. When would this not work is in graphene, but we'll go back to that later. So instead of writing the sum over neighboring states, we can say that we define this vector called the delta vector, which is the neighboring vector, which is...
Sorry, I think you still haven't finished discussing what the AKs are.
These are...
You wrote down what the AIs are.
Right.
But what are the AKs? Because in your assumptions, right, we only know what the ith lattice site states are, right? So these AKs you should be able to express the AKs in terms of these ith energy states, right?
But I'm trying to get the Hamiltonian with the AKs in them.
Yes, but you can still write down what is this AK dagger thing? How do I know that K inner product I is that thing? Because you just wrote that down. You just wrote down that the inner product of K with I is E to the minus IK dot Ri. Why is that the case? Where did I come up with that from?
It's a change of basis from position space to momentum space.
Okay, it's a moment. Yeah, okay, but what are the states then, right?
Okay.
If I have a change of basis, then I should be able to write one basis into one state in one basis in terms of states in the other basis. Okay, correct. There we go.
It's a test of my memory.
And this one has a minus.
Yes. Is this right?
Not well. Do I summation because we've been doing I everywhere, right? And then do you need like a square root 1 over n?
I think yes.
So yeah. And this should be like center of the board and boxed, and in like every possible color. Okay, maybe just put a box. Okay, correct. So what is this? I can define the state K. Do you agree? Where I sum over all of my lattice sites. I multiply e to the I k dot ri. So this is some exponential. Ri is the position of the ith lattice site, and I is just the state to be for the electron to be on the ith lattice site. Okay? And I can look at this linear combination. People agree I can write down this linear combination and I can look at it. Yes?
I thought K was a orthonormal vectors because it's
Yes.
the second.
Yes. So you can check that for different k, these vectors will be orthonormal. It's just that, in our assumptions initially we said let R Hilbert space be the electron is at Ri. We agree, like those things. So if I write down some new basis, I should be able to express the new basis in terms of the old basis. Do you agree? And so this is what she's doing here. So let's look at this linear combination and let's argue why this better be the right thing to look at. Okay? So where did all of this kind of begin with? The discussion started with a review of Bloch's theorem. Correct. Bloch's theorem said that if we have a translationally invariant Hamiltonian, there's a basis of eigenvectors of eigenvectors, which are both eigenvectors of the Hamiltonian and eigenvectors of the translation operators. Do you agree? Okay. So we wrote down for you a Hamiltonian, which is translationally invariant. Do you agree? So it commutes with all the translations by AI. Yes? Where AI are kind of the allowed lattice translation. Okay, very good. So this means that instead of trying to just diagonalize H directly, we should maybe rewrite it in terms of a basis of eigenvectors of the translation operator. Do you agree with that? So, right, we know that kind of H restricts on the eigen subspace of the translation operators. So let's instead rewrite H in a basis of eigenvectors of the translation operators. Okay? Does that make sense as a goal? And hopefully then the Hamiltonian will be easier to diagonalize once we write it in the basis of eigenvectors of the translation operator. Okay? And so now I write down this vector. This is some linear combination. I can write this down. This is going to be some vector. Okay, very good. And if I write this down, what am I going to get? If you look at this very carefully, so this is given some vector k, I get a vector like this, right? And what can I do with this? Well, you can notice that this vector is also itself translationally is invariant under translations. Why is this the case? Well, sorry, it's not invariant under translations, but it's an eigenvector of the translation operator. So you should show exactly how it is. You should show how TAI acts on this. Yes, you should write down TAI applied to K and compute it explicitly. It's not that bad.
But it's kind of trivial.
Yeah, exactly. So that's why you should write it down.
But I feel like I'm gonna get the notation wrong.
Okay. Okay. And now do TAI on this thing. Yes. Okay. Correct. Yeah. That's fine.
Okay.
Well, I
Not really.
plus. write I plus A. Sure. Do you agree? So do people agree with this? I just translate everything by my vector A. This is what that is. But then, okay, supposing that we have some periodic boundary condition, or we have like some infinite lattice, right? This is really the same thing, right? Yes. So there should be an eigenvalue that pops out of here somehow. Why is it not?
Shouldn't, like, if you write this thing, wouldn't there be an eigenvalue here?
Yeah, let me think about this.
Like, wouldn't you write this as like?
No. Why was it? I think maybe you don't act on the. Maybe you don't act on the exponential, but why would that be the case? I'm not sure. You should act on the exponential.
No, the exponential is just a number. It's not like the exponential is just a number. You don't like.
Oh yeah. Correct. The exponential is just a number, so you don't act there.
And then this thing here is. Yes.
Yes. And so, but now you can add, multiply by e to the ik dot a, and then divide by it to get back the same state. Right. So you have I plus a. To make it look like the old state, you want in the exponent to be ik dot ri plus a. Do you agree? So you multiply by that and divide by it. So plus a and then times e to the minus.
Actually, no, it would be
E to the
ik.
yes. Do you agree? Good. And so then you can shift indices in that sum, and then factor out the ik dot a. Well, don't add it there, and then write it on a new line and add the eigenvalue. Yes.
Here?
Factor it out of the sum.
Do I still write I plus a here for everything or not?
Well, no, you okay. Read, it's just happened, right? You're changing the.
Or J.
Sure, J. Just R and J.
Where we've done nothing but like J is equal to I plus a.
Yes.
From this step to this step, you just change everything that was I plus a. You change it to J plus to J.
Yes. And then you should rewrite this as the state we had before times the eigenvalue. Yes.
Oh no, this would also.
Yes, this would also be there. So just write equals and then write it down. Okay. Agree? So we wrote down this thing inspired by, Fourier transforms and change to momentum basis, and we realized, hey, this is an eigenstate of the translation operator. So in principle, I could have just written this down based on like some crazy intuition, like just if I was just so smart, I would just realize this would be an eigenstate of the translation operator. Wrote that down and realized, oh, crazy, it is. Right? And so remember the picture that we had, that I drew for Bloch's theorem last time, is that how do all of these like theorems kind of work? Is that I have my whole Hilbert space, right? And suppose I have H and T, which both commute with each other. Do you agree? Then you know that H preserves the eigensubspaces of T, and T preserves the eigensubspaces of H. So suppose you took your Hilbert space and kind of split it up into the eigensubspaces of T, right? eigensubspace of T. Do you agree? Then you know, for if these two commute, that you can think of H as an operator just on this, and then H as an operator just on this. And then instead of diagonalizing H on the whole thing, if you know what these eigensubspaces are, you can just separately diagonalize H on each of these subspaces. Okay? And so this is what we're doing. We found some, at least some, technically this should be all, of the eigenvectors of T, of the translation operator. And now we're just going to write down the Hamiltonian in such a way that we kind of separately write down a Hamiltonian on this, the Hamiltonian on this kind of part, on this kind of part, on this part, and so on and so forth. And then hopefully the problem of finding the eigenvalues of the Hamiltonian will be much simpler because we're looking at the Hamiltonian on a much smaller kind of subspace. Do people remember this picture from last time? Okay. And actually, in principle, one thing that you could have done is you could have done, okay, I know that these are my eigenstates I. Do you agree? And then you could have said, well, I know these are my eigenstates that are allowed, and say I want to find an eigenvector of this translation operator. Do you agree? So you could have literally just written down this eigenvalue equation and figured out that it has to be this. How could you have done this? Well, you just write down. So suppose I'm looking for an eigenstate. So looking for eigenstate of translation by A, right? And then you say, okay, suppose this eigenstate, whatever it was written as some linear combination like this. Do you agree? And then you said, okay, I want this to be an eigenstate, so I want to apply this to this and get the same thing back multiplied by lambda. Do you agree? And from this, you should be able to figure it out that these have to be the eigenstates. Right? You get some relation on the you get some relationship between the coefficients AI from these shifts, and you can figure out that it has to be this. 1 over root n is a normalization condition because you have n atoms in your lattice, and we also kind of assume that these I states are normalized, and that ij is delta ij. So it's an implicit assumption. So these are atomic orbitals. You know atomic orbitals.
Wait, if n is a number of atoms, then we cannot assume infinite crystal?
So yes, so you assume kind of there's some periodic boundary condition, or you can think of n in the sense of I'm taking n in some limit to infinity, and this is just I write this down before I've taken the limit. Or like n is very large, so surely in the bulk of your if you shift by a little bit and then you miss like some atoms, that won't affect anything too much.
Typical physics move.
Yeah, but so the goal is something like this, right? I find a Hamiltonian for which Bloch's theorem applies. I find the translationally invariant states. These are the translationally invariant states. And once I've done that, I rewrite the Hamiltonian in the basis of the translation of in the basis of states which are eigenstates of the translation operator, not invariant, eigenstates of the translation operator. And then hopefully the Hamiltonian will look simpler in that basis because Bloch's theorem tells you that it should look, probably simpler in that basis. Okay. And here we wrote down what the states have to be.
Right. So given everything we've just done, do these operators make more sense now?
And so, yeah, the operator AK is just something that takes the vacuum and creates that state. It sends the vacuum to that state, and the AK without the dagger sends that state to the vacuum.
So just as how in the position space we had these relations, in the momentum space version we would also have
you define these AK operators in this way, using those relations, and then you can, yeah, and then from that you can figure out a bunch of things. Let's see.
Alright.
Yes. Yeah, you can write.
Actually, I need to draw another picture. One last thing we're going to do in the position space is we're going to rewrite this sum over the neighbors as a sum over the sites and the vectors from the site to its neighbors. So, which would mean, say, like,
You should draw a picture.
yes, if I have site I here and site J here, and like, say it's a 2D square lattice, then the site I's neighbors, this sum over the neighbors of I would be these four states. Right, we're summing over the nearest neighbors. So instead of writing the sum as in like, okay, let's find all pairs of neighbors I and J, instead we do, let's find one site I and then define a vector delta, which is the vector from this site to its nearest neighbor. Then in this Hamiltonian, we can replace all the J's with a sum over the neighboring vectors delta of ai plus delta. Does this make sense? Does this make sense? And then because there's an overcounting factor between how you choose the sites like I and J, like there's some overcounting factor, so you divide this by 2. Because there's an overcounting factor based on how you choose your neighboring states. Like, yeah, like if I choose this, like the site J, then you would overcount this vector. Like the hopping between I and J, you sum over the pairs, but then based on where you choose your site to be, you get this overcounting factor. Right.
Something really unrelated, but I couldn't figure it out. So, the eyes and the bases, they run over what?
These eyes?
No,
These eyes.
the eye doesn't.
These eyes?
I is you have a lattice, you can index your atoms
Yes.
with some I.
Okay. So what happens if I multiply some AI with the J cat with I and J not being equal?
Like AJ on
Just
I.
zero?
Like
Yes.
this?
Yes.
That should give 0, right?
Yes.
Okay.
We assume that it's correct.
Because essentially right now, this is the model for a single electron. Right. So then from here, we can plug what we just found from here into that. There's 2 times 1 over n. Then you have e to the negative I k dot ri for this operator. I'll write the ak at the end. Now I need also the sum runs from I delta k and k prime. And then you also have for the other one, you have I k prime dot r I plus delta. And then literally plug and chug. But, okay. Next step is we can rewrite this exponential as e to the I k prime dot ri, and then multiply the e to the I k prime dot delta. Then there is an identity which you would have to believe me because I'm not going to prove that here, which is sum over.
I'm just going to put a box around it so it's not consistent. This is an identity, and just trust that the identity is as written.
Believe that.
Yes.
That's trust. Right. Then we stare at this and we see this is a negative ik dot r, this is negative ik prime dot r, and then we can apply this identity to basically get rid of the sum over like ri, like we get rid of the sum over ri and then the sum over k prime and k. The sum over k prime and k, we replace it with a delta function.
You should write everything down and write a delta function somewhere where is appropriate, and then write down the next step. So don't replace the sum just yet. Right? You have a sum over r somewhere, no? So above you should have a sum over r somewhere, right?
I.
Oh, I, okay. So we do the sum over I and we get a delta function, and so just rewrite the same thing, but replace the right thing with a delta.
The right thing is a delta function. Oh, okay.
Yeah.
I'm still skipping one step of combining the k's, combining exponentials here.
Sure.
Okay.
But write down the correct delta function and skip left steps.
So from this step to this step, we expand this exponential into two exponentials that you multiply, and then combine one of the k prime dot r with the k dot r, and then use this identity to get rid of that and the sum over r and replace it with a delta function. Right. And then from here, get rid of the n. And then from the delta function, we can get rid of one sum over k. So this k prime just becomes k. This k prime becomes k. This k prime. Okay, should have been k prime, but also becomes k. So you end up with a sum over only k and delta, which is to the ik dot delta. Exponential combined into a cosine, you end up with this form. So all this is basically saying that this is the Hamiltonian you end up when you go from the position basis representation to a momentum space basis representation.
Okay. So what's question to the audience after they're done writing? Why is this Hamiltonian so nice in this basis?
I think it's because like it's like translational invariant?
I mean, the Hamiltonian was always translationally invariant. Well, because it, from the beginning, we said it commutes with the T operators, and we showed that it does. So, look at this. Just look at this final line. What is so nice about this final line? In the quantum mechanics, what if we have a Hamiltonian? We always want to find the what and the what of the Hamiltonian. Correct. Okay. Well, look at this Hamiltonian. What are its eigenstates and what are its eigenvalues? So how does this act? How does this act on some state K? Let's say. It creates the same state. Is there any matrix element between K and some other K prime? No. This means that in the K basis, this is diagonal. Well, it's already diagonal. So this operator, as written, is diagonal in this K basis. Why? Because if I apply this to some state K, it destroys the state and then creates the same state back. And in the sum over K, any other K prime in the sum just sends the state to 0. So this is diagonal. So since this is diagonal, I can just read off what the eigenvalue should be. Do you agree? And I can read off, I can just read off what the eigenvalue should be. And I know what the eigenstates are. The eigenstates are there as written. Like that. Yes.
Generally speaking, this is like the energy associated with.
Now, once again, you write something down on the board in the midst of other completely unrelated things. And so either you need to put a box around it or you need to erase it. And it's nice. See how that box is of a green color? And so it's very easy to identify that box from the rest of it. You have many color chalks. Doesn't have to be green. It can be any color you like.
Sure. Right. This is just a general form of the Hamiltonian where you pack up the eigenvalues into this
From a diagonal.
Right. Right. Nice to work with. Now we do an example. So suppose you have a one-dimensional chain of atoms. And I pick a site I. What is the Hamiltonian? How would you write this Hamiltonian in the momentum basis? What would you need to find first?
You need to find the nearest neighbors.
Right, but we found an easier way. You find the neighboring vectors delta, because we're forgetting about this whole nearest neighbor things, because we're saying we can, in this Hamiltonian, everything is identified with the momentum and the vector from a site to its nearest neighbor. So in this case, if we say the lattice spacing is A, then the nearest neighbor vectors are just A and negative A. Right, and we kind of just plug this into that Hamiltonian, and then we get that the H for this would be negative T, and you sum over K. And this would be why do I have this? And you have the Hamiltonian for this system. There's also one that is only slightly complicated, which is like the two-dimensional square lattice, which is supposedly in the recommended exercise for this week, which I encourage you to try yourself because it's really kind of trivial. Right.
So calculation that we did there is really for a lattice in any dimension, 2-dimension, 1-dimension, 3-dimension.
The only constraint that is that it has to be a Bravai lattice, which is like your lattice has to be, you can go from any site to another site with one set of lattice vectors. And now we will do an example where that is not the case.
I feel like you erased that a little too quickly. Can you write it back down somewhere, maybe on top of the board, so that.
Okay. But that's
And
for
then
the
maybe
1D
if we
chain.
could, plot a graph or something.
Okay.
That would be nice. It's close to K plus close to -2. Sounds complicated. Oh, there's just two close K. Wait, it's close to -K. There.
Right, and then cos is an even function, so this is the same as cos Ka, you get a 2 up. And then in the dispersion relation, this is a word that I can use. You plot energy as a function of K.
Yes.
Yes. And this is negative, so it just looks something like, it's a bit shifted, but you get the idea.
Wait, should it be Ka instead of K? Like the, for example.
Well,
Some scaling factor.
A is a fixed number.
Right.
Oh,
Do you
okay.
agree? But what was A
A-
physically?
A physically is the separation between your 1D chain lattice.
Yes.
Like this distance is A.
And that's fixed. And so this is what people talk about when they talk about these bands in momentum space. If you rewrite your Hamiltonian, it's diagonal in momentum space, and you get that the eigenvalues depend on this momentum parameter, and so you can plot the energy as a function of K.
Like the band is this line here.
Yeah.
Suppose we had some dispersion relation which allowed us to draw like a different band. This would be like another band of higher energy.
But we will see that.
Yes. Can I erase this?
Well, you should erase the top band, and then you should take a sip of tea.
Okay.
You're not taking a sip of tea. Or
I
did you run out of
did.
tea?
I already did.
Still more tea.
I'll help myself.
I have another Earl Grey which maybe I should open. This French Earl Grey is getting kind of boring. Right, so is the overall idea of what we did kind of clear? We wrote down some Hamiltonian based on whatever reasoning, and we realized that it's translationally invariant. So then we applied Bloch's theorem and said, what are the states that are the translationally what are the states that are eigenstates of the translation operator, right? That's the question we asked. We realized that those states are those, the K's. Okay, and then we said, okay, well, if I rewrite my Hamiltonian in this basis of states which are eigenvectors of the translation operator, hopefully that will be much easier to diagonalize. And in this case, we rewrote the Hamiltonian in this basis, and it was immediately diagonal, right? Without much effort. Okay, but sometimes it's not immediately diagonal, but you get that the thing you have to diagonalize is maybe like 2 by 2 or 3 by 3 or 4 by 4, like a much smaller dimensional matrix than something with n sites, right? That's much easier to diagonalize a 1 by 1 matrix or a 2 by 2 matrix than an n by n matrix, where n is some large number, like Avogadro's number large. You know. Okay. Does people agree with this roughly?
Can I erase this now?
Sure. Maybe keep that.
Keep this one.
Yes, keep this one. Just for 5.
Okay.
Wait, sorry. The other thing that you can notice is that the energy is periodic in K in some way, right? Do you agree? Like I have a sum of cosines of delta del K, so there has to be some periodicity in K. And that's kind of expected, right? Because, remember, if I shift, for the people who did the suggested exercises from the blocks there, which none of you did, that's okay. If you look at it carefully, if I have k dot ri, I can choose a specific vector g in such a way that if I replace k with k plus g, I'm going to get a 2 pi I as a result. So it's going to just change everything by 1. So it's not going to change the angle state. So those states k are actually, there's certain vectors that if I add to k, I'll get back the same vector. And so I should expect that whatever I get should be somehow respect that periodicity. And okay, maybe it will.
Like the idea is that in this exponent, there's some k you can choose so that like e to the I k dot a is the same as e to the I k plus g dot a.
Yes.
So you get like different k vectors with the
just
same
write
vector.
down that the state k is equal to the state k plus g. So these states should be the same. You can choose a vector if you do the suggested exercises from last week. If you find the right vector like that, and you get that vector has to be the same as that vector. And so actually you can check that if these deltas are. Okay, so this is why I don't like introducing these deltas, because you have to be very careful about exactly what they are. In this case, they're exactly their reciprocal lattice vectors, and so you can get that that energy is periodic under shifts by that g as well. Okay, that's fine. And maybe just briefly discuss graphing, and then we.
Yes.
We will kind of review this again in the next.
Okay. So graphene. So what does graphene look like? It has a hexagonal lattice of the same type of atom.
Should have started drawing this more in the center of the board, so you could have hexagons. Or actually, if you can continue, I guess it would be fine.
Okay.
Okay.
Sure. But like for a given lattice site, it's the
Hold on, let people copy and. So, what do we want to do? If we have a lattice, we want to be able to pick some lattice vectors, AI, A1, and A2, such that I can write any point as a linear combination of A1 plus A2. Do you agree? So write that down somewhere. I want to choose A1, A2. A1, A2, such that any R can be written as some n this is what I want to do. And now let's try and do this for the graphing lattice. We see something goes wrong, and then we do something else. So suppose I started at the green point. What's one vector that I could try and consider? Like we have to figure out what these A1 and A2 are.
If we start from the green point, which vector would you have a guess as to be one of these A1 or A2 vectors?
So I can build the whole lattice out of these A1 and 2. Just guess anything. Okay, we can do 1 to 5, or let's maybe do green to 1 to 5.
I mean, yeah, green to 1 and then.
Yeah. Let's try green to 1 and green to 5, and see why that doesn't work. Okay. I want anything to be written as M1 A1, M2 A2, or M1 and M2 are integers. So suppose I went. Can you finish drawing the hexagon above? So now, suppose these were the reciprocal lattice vectors, the lattice vectors, they're not.
How would you go here?
Yes. How would you go here with that vector? Well, actually, not even that. Suppose I went twice up using the vector, that vector. There is no point there. Do you agree?
Right, like there's, if you went up.
Just try it, please.
Okay.
You have yellow, you're using yellow.
I'm gonna use a different one. This is a fake point, not a real point.
Yeah.
Like there's nothing here, but using this set, if you choose this vector as your A1, if you go up twice with this vector, there should be something there, but there is none.
Yes.
Which is why this is not a choice that
Yes.
would work.
Do you agree? So we can't choose these two vectors as our lattice vectors, right? Because otherwise, they give you some additional points which aren't actual sites on my lattice. Okay. So perhaps I can do this somehow differently. Okay, erase the fields and circle the green points and then circle the red points.
The red.
Well, you have 2 points.
Yes.
Circle the green ones and whatever other color you want. I always do like red and something else. I like that. Circle more of them. You have a big lattice. Okay. Looking at this, can people recognize a pattern? Just look at the green colors. What do you see? What kind of lattice? Say it louder. Yes. So there's a triangular lattice of green points. And there's a what kind of lattice? Yes, what kind of lattice? Also a triangular lattice, correct. And in fact, you can check that these lattice vectors are going to, the lattice vectors for the green lattice and for the blue lattice are going to be the exact same vectors. Do you agree? You can check, because the graphene is a honeycomb, it's a hexagon. And so the point is a hexagonal lattice. You can split into 2 triangular lattices. Do you agree? So just one centered around one atom and one centered around another atom. Right? And that's kind of how graphene is a little different from the cases we talked before. In the cases we talked before, we said there's there's a single there's a single site, which if I start at this site, I get all the other sites by going reciprocal lattice, not just lattice. So in the calculation we did before, we assumed that there's a single site, and I can get every other site from that one site. Here, I have 2 sites, and I can get every other site starting either from one site or another site. But this is a little bit different. Right? Here, I have 2 sublattices, an A sublattice and a B sublattice. What does this mean in terms of my my states? My states, this means I have states that are on the A sublattice and states that are on the B sublattice. And once I do just you say so.
remember we started this by saying that like this Hamiltonian has the same translational symmetries as the translational operators. In this case here, blue has its own set of translational symmetries and green has its own set of translational symmetries. So we can't. So when we write, if we want to write a Hamiltonian with the translational symmetries of the lattice, we can't use the same creation and annihilation operators. They would have to be different. And another thing to note is that the nearest neighbor, in this case, if we start from one lattice site, its nearest lattice sites are on the opposite lattice. It's not on the same lattice. So it's on the other sublattice, which means that when we write the Hamiltonian for this, instead of having the same type, the same set of creation and annihilation operators, they would have to be from different.
Well, that's not entirely correct, because the creation and annihilation operators in principle are the same. The only difference comes, so the Hamiltonian would be exactly the same, right?
But we want to define it with the
now
symmetries.
We have to be careful, because now we realize that in the way we talk about things, we have these two separate sublattices, and they're somehow different a little bit, and so we have to differentiate between these two sublattices. And so, what do these I and j mean? What you can do is you can say, okay, suppose I started off by looking at this pair of atoms, okay? This pair of carbon atoms. And if I translate this pair of carbon atoms using these vectors, then from this pair, I can get the whole lattice. If I translate this pair, I can get the whole lattice. Do people agree with this? Okay. And so now, I and j is the index of the pair. Do you agree? Right. So I can I can split this up into kind of these pairs of atoms, and index these pairs by I and j, and then yes, and then yes, and then use AI and AI dagger to talk about creating kind of the blue atoms, and BJ and BJ dagger and BJ of creating, say, the green atoms in the pair. Okay? The creation and annihilation operators, they still do the same thing. They create an atom at this site, destroy an atom at this site, create an atom at this site, destroy an atom at this site. It's just that now we want to differentiate between the blue atoms and the green atoms. And so to differentiate between the green atoms and the blue atoms, we decide to call the creation and annihilation operators for the green atoms like A, and for the blue atoms B, or whichever letters you choose. So there isn't actually any difference from this formula. This formula is the same as that formula. It's just that we're changing how we're indexing things, and we're changing that, okay, we want to now differentiate between blue and green. And so we just introduce different letters for blue and green creation and annihilation operators. So, because the symmetries of the two lattices are the exact same in some sense.
Yes.
Right? I just want to differentiate between the two lattices, so I introduce new lattices. But otherwise, the calculation is the same.
Yes.
Well, roughly.
Well, like if you look at this, and if you look at this formula, you will see that the dependence, like this formula doesn't really care about like which sublattice you're on, right? Because you're going from position space to momentum space. The momentum space doesn't really care like what your exact position is. So like whether you're on the green sublattice or the blue sublattice, when you're taking the operators like A dagger and A, or B dagger and B from that formula into the momentum space, you end up with the same set of momentum operators. So this like the calculation we did to go from here to here is basically the exact same, but then when you get to this point, like something doesn't cancel, so you can't just wrap it up in a cosine. But the basic idea is still the same.
What was the basic idea? We write down this Hamiltonian, then we have to do what? we have to find the states that are eigenstates of the pardon? Translation operators. Good. Those eigenstates are what? That thing. What's okay, but what's going to be different about that thing now? Now we're going to have states that look like that for what and for what?
These
So,
K
These
states.
Ks, we're now going to have states like that, but we aren't going to have one state like that. We're going to have two, for each K, we're going to have two states like that. One for what and one for what? Exactly. So one of those will sum over the A sublattice. And then I'll have another one that will sum over the B sublattice. So write this down over here on the right side. So I'm going to have K alpha and K beta. And just write down the exact same stuff. Why is that? Because the shifts are from the green lattice to the green lattice, right? So if I want something that is invariant under shifts of these B2, A1, A2 degree, then right, then the green lattice under the sublattice A, the green lattice gets sent to itself, and the blue lattice gets sent to itself. So one thing that's a little unclear in your thing is that actually the lattice vectors of the green and blue sublattice are the exact same lattice vectors. You just drew two different sets, but they should be the same. Erase those and then draw them on a different lattice set. Take, say, the top of the lattice. Yes, correct. Yes. The other one? And so now, in this calculation, what you would do the exact same thing. You would, this relation tells you how AI is related to AK, and BI is related to BK degree. And so then I would just rewrite that Hamiltonian in this basis, once again.
Also, here is n over 2 because there's two sublattices.
Yes, there's n over 2 because there's two sublattices. Good. And that's just to have the state normalized, so it's magnitude as well. Okay. So once again, you would use you would then write down. Yes, you would then write down something like this. You would express AI in terms of the AKs for one lattice and BI in terms of the BKs for the other sublattice. You would take this, you would plug it into here. At some point, you would use this relation somewhere to do one sum and get a delta function and get everything over one sum. And at the end of the day, do you remember what you get at the end of the day? I roughly remember what you get at the end.
I have
At the end of the day, you will be able to write down your Hamiltonian as, so, do you believe me that in principle I can, write something like that for A and B, plug it into here, do this, use this identity somewhere, and then get something in terms of K, like before. I know, this is not what I want you to know.
Oh, the other
I
one?
want you to write what I wrote down yesterday. Okay, I'll just write.
Like the
I'll get minus T, and what you will see, you will get A sub K dagger, B sub K dagger, matrix. The matrix is 0, 0, e to the minus I delta dot K, right?
Yes.
And here it's e to the I plus.
Yes.
Okay. Whoops. Sorry. I make the same mistake. This should be a row vector. Okay. Do you agree? This is a sum over K and over delta. So if you do this matrix multiplication, you still get like a a linear combination of these things, right? It's just that I wrote it down in a matrix way to make it easier to see what's happening. Right, like this would be AK times 0, BK times this, and then I'd times it by the AK dagger, BK dagger. But what's the point? The point is that here I'm going to have like I want things to be diagonal. Do you agree? Yeah, you can go. I want to write down my Hamiltonian to be diagonal in some sense, right? But if I expand this out, I'm going to have an AK and an AK dagger BK term and a BK dagger AK term. Do you agree? If I expand this out, this is not diagonal, right? Because this creates one state and destroys this destroys one state and creates a different kind of state. Do you agree? Right. So this means I have some. This is not a diagonal. This is not a diagonal operator. Do you agree? And okay, so the thing that's in front of here is precisely this minus t sum over e to the I delta dot k delta and then same sum, but maybe without the minus. Okay. So this is not diagonal. Yes? Like I'm saying, once you expand this, you will get this. And then instead of writing this, you can write it like this. And this is not diagonal. Okay. But you can see that this is not diagonal, but this is only a 2 by 2 matrix, right? Why? Because for a given momentum k, I have only two states. I only have a two-dimensional Hilbert space for one momentum k. Like the A sublattice k's and the B sublattice k's. So the k alphas and the k betas. So, and this is easy to diagonalize. This is a 2 by 2 matrix. You can find the eigenvalues fairly easily. And then you do it, you get like some square roots 1 minus cosine, something. And there's a lot more to say about it. And so what's the idea? So what does this kind of example demonstrate? The fact that you go to this basis of eigenstates of the translation operator, and you get that the Hamiltonian is actually not immediately diagonal in it. You have to separately diagonalize it again. It's once again the same picture that, okay, we diagonalized, we wrote it down in a basis of eigenstates of the translation operator, right? But then the Hamiltonian, while it preserves the subspace, it might not necessarily be immediately diagonal on the subspace. So then you have to separately diagonalize the Hamiltonian on the subspace. And this is what you do by diagonalizing this matrix. So yeah, this is roughly the idea. We find the Hamiltonian that's translationally invariant. We say that there has to exist the basis of eigenvectors of both H and the translation operators. We find what the eigenstates of the translation operators are. Right? Rewrite the Hamiltonian in terms of this basis instead of the previous basis. And hopefully the Hamiltonian is simpler in this new basis than it was in the old basis. And indeed, this is a lot simpler than this. Right? Because this is some 2 by 2 matrix for each k that I need to diagonalize separately. This splits the Hamiltonian into a block diagonal thing. This is something more complicated, where a lot of things get coupled, versus here you get coupled only for the same k. And this is easier to diagonalize. We will discuss this, I think, again a little bit the next physics week. This maybe a bit more than I was hoping it would be. And I will write up suggested exercises where you will get to do like a very simple, some simple practice of just doing this computation by hand yourself. Okay. But do people see kind of how graphene was a little different from maybe the square lattice? Because now you have to, your lattice isn't like one lattice, it's really two lattices. So you get a kind of two-dimensional, like the basis. There's 2 bits to it. So then you get 2k, 1k for the alpha and 1k for the beta, and that's why you get this 2-dimensional matrix. This is kind of k alpha goes here, k beta goes here, and k alpha comes out, k beta comes out. Yes. Right, so because we have these 2 sublattices, we get in the end a 2 by 2 matrix instead of okay. All right. Do you have anything else to say? People see how graphene is different from like a square lattice. Good. So in that case, we'll stop here. I have an off